Hi all, welcome back. Um, Today we are going to talk about polynomial interpolation, and finally we will jump into the word polynomial interpolation, which is a bit different from what we have been doing till now. So let me explain what we have been doing and what we will do today. So first is that in Taylor series we had a point, so x0. We knew the value of the function at that point, also the derivatives, f prime and f double prime, and maybe some more, up to some finite order, right? And then what we did is we predicted it for some other point. All right, and we just needed the information from one point, but we needed multiple informations, like we needed the value of the function, the value of the derivatives. Now in polynomial interpolation, what we will do is that we will have not just one but multiple points. So we call them nodes. So we will have multiple nodes. Let's say these four. All right. And now what we want to do is that we want to find a polynomial. Let's say this, which goes through the points. So what we can do now is that let's say that I want to find the value at this point. Then I have this polynomial, this polynomial, and this gives me the value of the approximate, up to some error, the value of the function at this point. Let's call this x prime. Okay, so this is the goal of this section today, is that we will find a polynomial that goes through all the nodes that I have in my information. Okay, so let's do it. Let's say I want to find a polynomial of degree n. Okay, so a general polynomial of degree n, Pn of x, can be written as a0 plus a1x plus a2x square goes up till an x to the power n. Correct? So we can write it in a shorthand form. We can write it for k going from 0 to n. We can write it ak x to the power k. Okay, now we have to understand that if I want to find a polynomial of degree n, then we need to know all these coefficients, right? So we need to know from a0 to an. And how many of them are there? There are n plus 1 of them, right? Because you have started counting from 0. All right, and what are the conditions that this polynomial has to satisfy? The polynomial has to satisfy the okay, let me write it in a different color. Let's say the conditions. So the conditions that the polynomial has to satisfy is that the polynomial at x0 should be equal to f of x0 at the node, right? Because I said that I want to find a polynomial which goes through the point. So at the point, the value of the function and the value of the polynomial is same. It is true for all the points. Okay, so the value at the point x0 should be the same for the function and the polynomial. Same goes for x1 up till and f of x1. And you can go on, and it has to satisfy till what? Okay, now if I want to find a polynomial of degree n, then I need to find n plus 1 coefficients, right? So to find n plus 1 numbers, I need n plus 1 conditions, right? If you remember from your linear algebra course, that if you want to find out 10 coefficients, then you need, or 10 unknowns. 10 unknowns is the right word. If you want to find 10 unknowns, you need 10 constraints, 10 linear constraints, right? So we need at least, that means that I need n plus 1 nodes to find a n degree polynomial. So that means that I will have x0 up till xn, and this will give me a polynomial of degree n. So it depends on the number of nodes. If I am given 2 nodes, I can have 2 conditions and I can only calculate 2 coefficients. That means a0 and a1. That means I can get a straight line. Okay. If I am given more conditions, more nodes, then I can generate a higher degree polynomial. So it actually boils down to the number of nodes I'm given. That means the more information I have, the higher degree polynomial I get, and the higher the degree of the polynomial, the more precision I get. Okay, the error is less. So I hope this is clear to you. And now let's work out an example. So let's work out an example. The example is that, let's say that n is equal to 1. Okay, so what does it mean? That means that you have 2 nodes, which is x0 and x1. Remember, we start counting from 0. When n is equal to 1, I have 2 nodes, x0 and x1. And what else do I know about it? I know f of x0 and I know f of x1. That's it. I don't know how the function looks like. Okay, this is the idea of polynomial interpolation, is that I don't know how the function looks like, but what I know is the value of the function at some point. Okay, and now if I am given 2 nodes, what is the degree of my polynomial? My degree of polynomial is 1, right? Because you see that if you are given n plus 1 nodes, you get a polynomial of degree n. So if you are given 2 nodes, then you'll get a polynomial of degree 1. So my polynomial p1 of x will look like something like this: a0 plus a1 of x. Okay, so now I need to find this a0 and a1 from these given numbers. These are the numbers I know, and I have to find these two numbers so that I can get the polynomial. Okay, so how do I do that? I need to use the conditions. This is the basic trick of polynomial interpolation, is that my p1 at x0, what is this? This is a0 plus a1 of x0. But the value of the polynomial at the node x0 should be the value of the function, which is f of x0. Alright, this is my first condition. Second condition is that the polynomial at x1 should be equal to a0 plus a1 x1 should be equal to f of x1. Right? These are the 2 conditions I have. Now you can see that I have 2 conditions. Here I know x0, I know x1. I know f of x0, I know f of x1. So I have to solve I have to find 2 unknowns, which are a0 and a1, and I have two conditions, which are these 2 equations. So everything is perfect till now. Okay, how we can solve these equations, this set of equations? This is very easy. You can add them and subtract them, and you can find them out. So let's try to work that out. Let's say we want to subtract that. If we subtract these two, these two will be cancelled. Okay, and what we get is a1 x0 minus x1, and you get f of x0 minus f of x1. And if you divide, then you get f of x0 minus f of x1 divided by x0 minus x1, and we have got a1 in terms of all my known data. So I know this. Okay, I know everything in the right hand side, so I know a1. Now if we substitute it back here in one of the equations, we can get a0. So let's do it. A0 plus a1 x0. So a1 is f of x0 minus f of x1 divided by x0 minus x1, and I'm using the first equation, so into x0 is equal to f of x0. Okay, so I need to take it on the other side. So a0 is equal to f of x0 minus x0 minus x1, and you have x0 f of x0 minus x0 into f of x1. Okay, now we have to do some algebra. So if you do that, x0 minus x1, then you have this f of x0 into x0 minus okay, let me write it in the same order so that it's easier for you to understand. So x0 times f of x0 minus x1 times f of x0 minus x0 f of x0 and plus x0 f of x1. So two of them cancel. Which two? These two cancel. Okay, so what we are left with is just x0 f of x1 minus x1 f of x0 divided by x0 minus x1. So this is my a0. Okay, now you can also check that we know everything on the right hand side. So we have calculated a0 and a1. So now if we plug that in this equation, then we will get the polynomial. All right, so we have found the polynomial once we have two nodes, which is a straight line. Okay, but doing this algebra for many more variables it's more difficult, so it's better to write it in a matrix form. So for example, once we had this box, we can write this set of equations with matrices. For example, I can write this as 1 x0 1 x1, and you can write it as a0 a1 is equal to f of x0 f of x1, right? So if you multiply them out, you'll get these set of equations. So let me write it in a clear manner. So for two variables, I can write it a1 x0 1 x1. You have this a0 a1, and you have this f of x0 and f of x1. Okay, so the best way to do this is we have to find a0 and a1. So we can just invert this matrix, a0 and a1. You can find the inverse, 1 x0 1 x1 inverse f of x0 f of x1. Okay, so how to find the inverse of a 2 by 2 matrix? I think all of you know it, which is 1 by the determinant. So this determinant, okay, let me write it down. 1 by the determinant of the matrix and times x1 1 and you get minus x0 minus 1, right? And you multiply by f of x0, f of x1, and if you multiply them out and calculate it precisely, you will see that a0 and a1 will give you the precise results that we calculated before. I leave it to you as an exercise because you calculated the inverse of a 2 by 2 matrix before. So do it, check it by yourself, and check that these two equations are reproduced by this calculation. Okay, I hope you can do it. So now, this was a simple case when we had to calculate the polynomial from just two nodes. From two nodes, the degree of the polynomial was 1, right? So what if it is general? That means that I have x0, x1 up till xn. Then what will be the degree of my polynomial? Now you can see that I have n plus 1 nodes. That means that I can get n plus 1 conditions or constraints, and that implies that I can calculate n plus 1 coefficients, coefs, and that implies that my polynomial will be of degree n, because this means that a0, a1 up till an, these are the coefficients I can calculate. Okay, so how do I calculate it in a formal manner? So the way to do it is that I know these nodes. That implies that I know the value of the functions at these points. All right, so if I know the value of the functions at these points, then let's write down the conditions. What are the conditions? The first condition is that the value of the polynomial at x0. That means that my polynomial Pn of x is in general a0 plus a1x plus a2x squared plus up till an x to the power n, right? So my conditions are that Pn at xi means the nodes, I can be from 0 to n, should be the value of the function, right? That is the principle that we have been using. Please remember this is very important. This is how we do polynomial interpolation, and this will be used throughout this chapter, and wherever you need polynomial interpolation, you will use this. Okay, so now let's calculate the constraints. The first constraint is that the first condition is that a0 plus a1 at x0. That means I'm calculating the polynomial at point x0 plus up till an x to the power n, x0 to the power n should be equal to f of x0, right? On the left hand side we have written the polynomial and we have evaluated the polynomial at point x0. Similarly, the polynomial at x1 will be a1 x1 plus a2 x1 square plus up till an x1 to the power n, and this should be equal to f of x1, right? And same goes for x2, a1 x2 plus a2 x2 square plus up till an x2 to the power n should be f of x2. And if you keep on going, it will end at some point, and that is a0 plus a1 xn, which is the last node, and a2 xn square plus up till an xn to the power n. Please remember that this is just a subscript and this is the power. Okay, and this is equal to fxn. Okay, so now obviously this is a very complex equation, but we can write it with matrices, and that will be very easy. So with matrices we can write these set of equations like this: 1 x0 square up till x0 to the power n, 1 x1 square up till x1 to the power n, 1 x2 square up till x2 to the power n, and the last one, which is 1 xn square up till xn to the power n. And if you write this, this will be a0 a1 up till an, and the right hand side will be f of x0 f of x1 up till f of xn. Okay, so this is the way to do it. Write it in a more compact way with matrices. So now there are some names. So now the general technique is pretty simple, is that we have to, okay, this matrix has a name. This name is called Vandermonde matrix. Vandermonde matrix. Okay, so our goal will be to find these coefficients. So what we have to do is that, let's call this big matrix V, this matrix A, and this matrix capital F. Then this equation can be written as VA is equal to F. And to solve this equation, because we have to find this A, then A will be equal to nothing but V inverse of F. So now the task, and you can see from here that I know all these numbers because I know x0, x1 up till xn, so I can calculate their powers. I can easily calculate their powers. So I know every single element from this matrix V. So once we have calculated all the numbers here, we can calculate the inverse. So then we can get A. But there is a condition, that is, this matrix V has to be invertible. Otherwise it won't be solvable, right? So what we know from our previous experience from your linear algebra course is that V inverse exists if and only if determinant of V is not equal to 0, right? And determinant of V can be written as a product of 0 is less than or equal to I is less than j is less than or equal to n xi minus xj. So if you don't understand the notation, let me explain a little bit. This is, you know, this sum, right? The sum over n, from n goes from 1 to 3, means that this is 1 plus 2 plus 3. So the product of n from n going from 1 to 3 is that 1 into 2 into 3. Okay, so if you want to expand this out, let's say the first term would be x0 minus x1, you will have x1 minus x2 and all possible combinations. Okay, xn minus 1 minus xn, something like that. Okay, I is less than j, so I is less than j. Okay, yeah, it's correct, the last one. So you'll have a lot of products, but it can only be non-zero because I said that V inverse exists if this determinant is non-zero, and this will be not zero if and only if all the nodes, that means xi is not equal to xj if I is not equal to j. That means that all the nodes are distinct. All right, so if if I have x0, a point in my graph x0, no other node will be the same. That means that x1 and x0 will always be different. x2 will be different from these two. Okay, so this is the idea, that all the nodes have to be distinct for V inverse to exist. Okay, so this was the idea, that all my conditions were summarized with this matrix equation, and then all we had to do is to find the inverse of this big matrix V, and then it was solved. Okay, and in general, finding a matrix, the inverse of a matrix, is not so easy. When I mean, especially when it becomes big. For example, if you have 100 nodes or 1000 nodes, then it becomes really difficult to find the inverse. So there will be other techniques rather than this, but this is the most basic one, and we will try to work out an example in the next video, and then move on to some other techniques in the following lectures. Okay, thank you so much for your attention.